Dear researchers, scholars, Science Father Organization Committee, my name is Dr. Fang Wenjun from College of Mechanical and Electrical Engineering of Changsha University, China. It's my honor to be awarded the Best Researcher Award. This presentation video is about composite materials. This topic is improving antistatic and mechanical properties of glass fiber reinforced polypropylene composites through polar absorption and the anchoring effect of organic salt. This report contains 6 sections. The first section, Introduction. Research background. Why does polypropylene need antistatic treatment? Causes of electrostatic charge. Intrinsic characteristics of low dielectrical constant and high surface electrical resistance. Thus, these defects result in many hazards. Scholars have taken measures. The effect approach is blending with antistatic agents with polypropylene. Then, we should consider the comprehensive results produced, such as crystallization behavior, mechanical properties, and even antistatic performance. Next, we review the research progress of antistatic composite materials. We found many conductive alternatives in fiber-reinforced polypropylene system. Carbon black was used. However, this type filler need more content than using carbon nanotube. However, the dispersion of nanotube requires a complicated pre-treatment process. Further, nickel-coated glass fiber were used as conductive fillers to form a three-dimensional conductive network. However, this process involves some toxic material. Therefore, a promising organic salt emerged. Previous research found the population threshold of solar fiber reinforced polypropylene composites after adding organic salt is 0.25 weight%. Moreover, previous research used traditional high viscosity and antistatic polypropylene as a matrix and only explored the tensile strength. Nevertheless, there are still many technical gaps. Such as crystallization behavior, the arrangement model of conductive particles, and the reasons for the increase and the decrease in the tensile strength. The chemical interaction mechanism among amine small treated non-glass fiber. The other crystallization performance, such as nuclear and crystal growth rate, crystalline size distribution, phase, and laminar thickness, as well as crystallinity. Polypropylene rendered polymer with high weather resistance, no temperature breakage, lower viscosity as a matrix. Therefore, The aims of this represent study are twofold. One is to prepare antistatic fiber-reinforced composites with a lower pollution threshold. Another is to explore how organic salt affects the crystallization behavior and interface, as well as conductive modes. The second section, experimental, will adopt intersection molding process to prepare antistatic long-glass fiber reinforced polypropylene random copolymer, which contain organic salt. The corresponding physical, chemical, and mechanical properties, characterization, equipment are as follows. The third section, results and discussion. 3.1 Interaction among organic salt matrix and fiber. Using Fourier transform infrared spectroscope to explore the interaction between the various components in the system, we found that a hydrogen bond is formed between the groups of organic salt with the groups of long-glass fiber. 3.2 Antistatic performances. We further explored the antistatic properties of the fiber-reinforced system. We found that adding 0.15 weight% enhanced the electrical conductivity of the composites to the lowest value of electrical conductivity of the antistatic materials. This suggests that the preclusion threshold is 0.15 weight%, which corresponds to the formation of a continuous conductive path. Next, we give the schematic of the conductivity improvement mechanism based on the length effect and the space occupying effect of long glass fiber. First, the length effect of non-glass fiber. Compared to short glass fiber, the length advantage of long glass fiber allows a longer conductive path to be created after fewer lifetimes, which makes it easier for adjacent conductive paths to be connected, thereby forming more crossed conductive paths. Second, the space occupying effect of long glass fiber. We can divide the conductive particles in the matrix into several units. Then the junction of units is regarded as the position to be replaced by the non-glass fiber. After adding non-glass fiber, the conductive particles organic salt at the original junction are squeezed into the original unit area, thus increasing the unit density of conductive particles and reducing the distance between conductive particles without increasing the content of conductive particles. No isothermal crystallization and subsequent melt behavior. From the crystallization curves of our samples, we obtain the relatively important crystallization parameters, such as the crystallization peak temperature, current structured temperature, overall rate of crystallization, nuclear rate, and size distribution of crystallites, respectively. We have found the evolution of these parameters. According to these parameters, a schematic diagram of the nuclear mechanism is given. homogeneous nuclear for neat matrix. Long glass fiber divides a large and complete matrix region into many small units, which hinders the movement of the chain segments. Adding 0.05 weight% organic salt significantly improves the nuclear rate by 19.3 weight%, suggests that organic salt can enhance the heterogeneous nuclear. Adding 0.15 weight%, a conductive path has been formed. The nuclear rate decreases, implying that organic salt and long glass fiber generate competitive nuclear. Continually increase the organic salt. The nuclear size increase while crystallization rate decrease, implying that the free space for movement of the molecular segments in the matrix is squeezed. Then the organic salt content is 0.35 weight%. More conductive paths are formed. The content of the organic salt in the matrix was also large enough, which further squeezed the active space of the chain segments. The crystallization rate was also reduced. We further studied the microstructure of composite material, such as type of phase, the thickness of the laminar crystal, and the growth direction of the laminar, and obtained the evolution law, which laid the foundation for establishing the relationship between each of the mechanical properties. Through the tensile mechanical performance test, we obtain the stress-strain modulus of different composite materials. The tensile strength first increased and then decreased with the increasing antistatic agent content. Tensile strength reached its maximum value at the 0.05 weight%. As the given antistatic capacity, such as 0.15 weight%, the tensile strength was also improved. In comparison with the long glass fiber reinforced. The level of mechanical properties is further confirmed from the archaic quality of the fiber matrix interface and the organic salt and the matrix. Archaic quality of fiber matrix interface in the non-glass fiber in composites increase first and then decrease with increasing organic salt content. Adding 0.05 weight% organic salt, the fiber matrix interfacial gap disappears, and the interface is tightly bonded. Integrating crystallization behavior, crystal structure, mechanical properties, and failure mechanism, we draw a schematic diagram of interface strengthening and antistatic mechanism. First, without organic salt, the surface of long glass fiber cannot form a proper holding force, thereby causing the fibers slip, and fracture under the tensile loading. After adding 0.05 weight% organic salt, organic salt has an anchoring effect on the matrix. The relative longer contact area between organic salt and the matrix generated a stronger anchoring effect. When the content increases from 0.15 to 0.35 weight%, a close arrangement of organic salt at a concentration of 0.15 weight% on the glass fiber surface made the composites that having a proper antistatic capacity. Nevertheless, this also reduced the effective contact area between organic salt and the matrix, decreasing the anchoring effect. Our work is expected to gain a new understanding of the crystallization behavior of the matrix enriched by organic salt and provide some fundamental data for further study for achieving better antistatic and mechanical properties. That's all. Thanks to all scholars, researchers, and the Science Father Organization Committee. Thank you very much.